So in today's lecture, we're going to be talking about alkene chemistry. So everything from its structure, naming, isomerism, and reactions. So let's first look at the naming of alkenes. How do you name alkene? So an alkene is an organic compound with a double bond. So you could have something as simple as this. So this is essentially just two carbon atoms. If you see the naming video, you would know that the prefix for two carbon atoms is ethene, right? Eth. Now, because we have a double bond, that is denoted by an ene. So it becomes ethene. If I have another substituent on it, then I will also have to take care of that substituent when I name it, right? Suppose if this was a chlorine instead. So this would be chloroethene, right? And so on. And then also the position of the double bond, right? So whether it's on the first carbon, whether it's on the second carbon. So suppose if I had a structure like this, would I have more than two carbons, right? And this is a double bond. By the way, what kind of structure is this? What kind of formula? This is a skeletal structure, right? And then what do? You start by naming, numbering the carbons, and you make sure that you have the lowest number for the functional group, right? That's what we always do. So that's what is going to apply to your double bond as well. So I'm going to start naming from here. So this is 1, 2, 3, and 4. So this is going to be 2. And what do we have? We have bute, right? So this is going to be 2-butene. Some textbooks like to call it bute-2-ene. So both of them are correct. Both of them are accepted by IUPAC. So whatever suits you, you can work with it. Next, we're going to talk about isomerism. So there are two kinds of isomerisms in alkenes. We have structural and we have geometrical, right? So what is structural isomerism in alkenes? It is the position of the double bond, right? So whatever carbon I have. So suppose if I have a pentene, right? So this is 2, 3, 4, 5. Suppose if it's on the first, or if it's on the second, right? Or maybe I have a branching. So I have a branching right here, right? So I have a CH3. So depending on the position of my double bond, so this would be pent-1-ene, right? This is going to be pent-2-ene, whereas this is going to be what? So this is 1, 2, 3, 4, right? So this is a butene, correct? This is 1-butene, and then I also have a methyl, right? But I'm going to start numbering from here. So this is 1, 2, 3. So this is 3-methyl 1-butene. So this is your structural isomerism. The other kind of isomerism that we have is geometrical isomerism, and this is more interesting. So this is found in some, but not all alkenes, right? And it occurs due to the restriction of the rotation of the double bonds. So you can see in the first image, right? So this is a single bond. So single bonds, they can rotate quite freely, right? But double bonds, the movement is restricted, right? So if I were to say, for example, have different groups on one side and another set on the other side, right? This is called a geometrical isomer. Let me explain this further. So we have two kinds of geometrical isomers. We have cis and we have trans. So on cis, when you have the same groups on one side, we call them cis. You can also say Z, right? That is also another way of naming them. If you have these groups on either sides, we call them trans. So this is trans because these groups are on opposite sides, right? So cis and trans. Now let's see, is this a geometrical isomer? Is this cis or trans? Yes, because I have two different groups, right? Let's try to name this. How do you name that? So this is basically How many carbons? 1, 2, 3, 4, right? I believe the green ones are carbon. We could assume otherwise as well. So let's assume they're all carbons, right? And so this will be butene. And because the groups are on the same side, we're going to call this cis butene, right? And if I had like trans butene, they will be on opposite sides, right? Okay, let's look at the second one here. Is this a geometrical isomer? So this is a geometrical isomer, right? So we can put a tick there. Is the second one a geometrical isomer? No, because when you have groups on the same side, so these are attached to the same carbon, right? You cannot have a geometrical isomer in that case. All right, let's look at the next one. Do we have a geometrical isomer here? No as well, because you have two groups that are the same on one side. So this is a no as well. What about the last one? Yes, this can be a geometrical isomer. So it's not necessary that these two groups have to be the same. They could be different. I could have one CH3 and I could have one C2H5, and it still works out. So this is going to be a geometrical isomer. Now we're going to talk about reactions, right? The main reactions that an alkene undergoes is addition. And why is that? Because you have a C double bond C, right? So we have a C double bond C, right? And why is that double bond occurring? Because you have this p orbital overlap. This p orbital overlap basically means it has high electron density, right? So it attracts a lot of these species called electrophiles. So electrophiles are basically species that have a partially positive charge and a partially negative charge, right? Which basically means it has one of the elements which is more electronegative than the other. So it tends to pull the charge towards it, right? That's what is denoted by this arrow. So whenever you have an electrophile, they can help undergo addition reactions in your alkenes, right? Examples of electrophiles are hydrogen bromide, hydrogen chloride, all of your hydrogen halides, right? And things like H2SO4. So all of these are electrophiles. Electrophile means electron loving, right? So it's looking for a center that is filled with electrons. So this is a particular mechanism that most, or actually all of the electrophilic addition mechanisms follow. So you would have like a double bond in here, right? So the positive side gets attracted to this double bond, the electrons move. These arrows that you see in chemistry, right? These curly arrows, they basically show you the movement of the electrons, the path the electrons take. Where do they get transferred? So they get transferred from the double bond to this positive, positively or partially positive charge, right? And so this guy attaches in here, right? That's what we see. So it's got attached there. And the other carbon now has become a carbocation. So that gets attacked by the negative center, right? And then you end up with this compound, right? That kind of mechanism is what is followed. Now let's look at reactions. We want to first start with something very simple. That is just the addition reaction of hydrogen. And I really want you to note this down. If you don't already have notes, please take notes while you watch the lecture. So you have an alkene, which is like a CH2, double bond CH2, and I'm adding hydrogen on it, right? So what is this? This is an ethene, right? So this is an ethene. I'm adding hydrogen on it. And this is done in the presence of a nickel catalyst, right? And what happens? The hydrogen gets added onto the double bond, right? So this was my CH2, CH2. So this is going to break up, right? Sorry, just going to erase that really quick. And I'm going to change back to my pen. Okay, so this is going to break up. the pi bond breaks up, the double bond, and then it opens up and you have your addition of hydrogen across the double bond. And now you end up with what is called an ethane. So whenever we have addition reactions of hydrogen, we change from alkene to alkane, right? In this, you don't necessarily have the whole concept of electrophilic addition going on, but this was just the first reaction that I wanted to talk about when we talk about addition reactions of alkenes, right? So it is the changing of alkenes to alkanes. Okay. The next thing is basically the addition of steam. So how is steam added is you have the same thing. You have, an alkene, you add water, and you have a catalyst, phosphoric acid, right? So your phosphoric acid, and then that gives you ethanol. So you basically start with an alkene, and you end up with an alcohol. So you have to basically memorize these reactions, right? And as you go, and as you keep memorizing them, everything will make sense to you. When you finish your syllabus, everything will come together like pieces of a puzzle. And it's fun. Okay, so here I have a quick graphic for you for the addition, electrophilic addition of HBr. So the small white thingy is your H and this is my Br, right? So what happens? This is basically partially positive. This is partially negative, right? Because remember, it's an electrophile. So what is going to happen? The electrons are going to move from here, and then they're going to move towards the bromine, right? And then this guy is going to attach onto this carbon, leaving a carbocation. And then this guy is going to go up here, and attach right here, right? So what am I going to get as a product? So I'm going to get something like this, right? So this is my Br, and I have my carbons and my hydrogens, right? So I'm going to end up with this. What is this called? This is called so I have a halogen, and this is an alkane, right? So this is a halogenoalkane. Okay. So this is just your electrophilic addition of HBr, right? On a normal primary alkane. So this is what you have, and this is what you are going to end up with. I should have probably just used this image. Okay. But what happens when you have unsymmetrical alkenes, right? Something like a propene. Then what would happen? Well, you have the possibility of two products forming. So either the Br attaches here or it attaches here. Now, what is going to decide which is going to form and which is not? Or are both products going to form? Or are they going to form in equal amounts? What happens? Right? So this is where the magic of Markovnikov's comes in. Markovnikov's rule. Right? So what is my Markovnikov's rule? It basically states that the most stable carbocation is going to form. Okay? So let's look at our carbocations, right? Which is more stable, which is not. Let's see. So we have our methyl, and then we have, a primary. So why are we calling this a primary? Let's look at that first. So this is a carbocation. If it's attached to only one of the carbon, we call this primary. This is another carbocation, but this is attached to two others, so we call this secondary. This is another one, but this is attached to three others, and we call this tertiary, right? Now, because this is attached to three others, and it's tertiary, so this charge, right, this positive charge is basically stabilized by these carbons that are attached to it, because they sort of like push their electrons towards the central carbon, right? So they're giving it all the support it needs. They stabilize the positive charge, right? So this is the most stable. Now this is more stable than a secondary, because secondary, I drew the arrow reverse. Secondary has two carbons to lean on, right? It has two good friends. So it's more stable than my primary. My primary just has one poor friend to lean on. But you know what? My poor methyl, is my least stable. And you know why that is? It's because it has nobody to lean on and to stabilize its positive charge. So this is my least stable. This is my most stable. Right? So you need to keep this in mind when you are going to think about your reactions, right? Think about your stability of carbocations. By the way, this primary, secondary, tertiary thing, that applies to all kinds of organic compounds, right? And you will see that when we talk about alcohols and things like that. Okay. All right, so let's look at this reaction again, right? So now we're going to decide which one is going to be your major product, which one is going to be my minor product, right? So the same thing happens in both the reactions. You have your double bonds moving here. This is partially positive. This is partially negative. This is going to move here. The same thing applies here, right? Quite understood at this point. So you have an electrophile. But now we want to talk about the carbocations, right? So this guy here, he's attached to two other carbons, right? So this is what kind of a carbocation? This is secondary, right? But let's look at this one. So he is attached to only one other carbon. So this is a primary carbocation, right? So this is primary, whereas this is secondary. So what would happen? So this guy is going to attach here. The same thing is going to happen for the primary. So this right here is going to be my major product, because obviously the formation of a secondary carbocation is going to be favored. But the second one will still form, but this is going to be called a minor product. Okay. Then next we have the electrophilic addition of bromine. This does not require a catalyst or UV light. It happens at room temperature. So what happens is you have bromine. When it approaches the double bond, right, you have this sort of electron transfer going on. So a lot of times students would ask, why does this happen, right? Because bromine is nonpolar, isn't it? So why does this happen? So let's look at that first. So this is my normal nonpolar bromine atom, right, enjoying itself. But what happens when it approaches a double bond, right? This electron density that you have here, you remember the electron density that we saw at the start? That starts to push electrons, right? So the electrons that were here of bromine, they sort of feel this repulsion, right? And they get pushed away. They get pushed away, and it's as if the electrons get pushed away towards the upper atom. So this guy, the bromine that's closer, starts acting like a partially positive center, whereas the bromine that's at the top starts to act like it's partially negative, right? So this is what leads to this reaction of nonpolar bromine. So what happens? The electrons get transferred from here to here, then from here to here, and then obviously the first bromine attaches. This gives rise to a carbocation. The second bromine attaches, and you get a nice, added bromine compound. And this is going to be called what? This is going to be called an alkane, but this is also a halogenoalkane. And you have dibromine, right? So you have dibromine, dibromoethane. That's what we're dealing with here. Okay, then let's look at some really cool reactions of alkenes, which are quite simple. So if you have an alkene and it's cold, dilute acidified potassium magnate is added to an alkene, you are going to end up with a diol, right? But things change when you are adding a hot concentrated potassium permanganate solution, right? Now, when you add hot concentrated, you will have to look at the type of alkene you have. If you have a primary alkene, remember? So double bond attached to only one other carbon. If you add this to a primary alkene, you're going to get complete oxidation, and you end up with CO2. But if you add the same thing to a secondary alkene, right? a secondary alkene, which means it's attached to two other carbons. So the first step, you're going to get an aldehyde, right? But if you leave it for further oxidation, you're going to end up with carboxylic acid, right? So there are two steps when you have secondary alkene. But when you have a tertiary alkene, so which means it's attached to three other carbon atoms, you're just going to end up with a ketone. So this thing is going to slice from here, right? So you're going to end up with a ketone here, and then you would have another aldehyde or something like that right here, okay? And then also you have your addition polymerization. So this is my alkene. When it polymerizes, you have lots of these monomers that attach to each other. So this is going to be my polymer. And you also have something like this for chloroethene. So when you do the polymerization for chloroethene, you end up with polychloroethene. This is also called PVC.